So this stuff is all from 14.3, which is motion in space. And just to give you a little bit of background, I'm going to talk about a couple things in 14.2 because they'll help us. So R of t is a vector, we're going to call it a vector valued function. And it's going to have components that now have variables in them. So we've, since day one, we have dealt with vectors, but they've always had constants in there. So like v equals 3, -1, 5. This is exactly the same, except we don't really call them v anymore. Since they're functions, we use function notation. That's what the parentheses t means. It means we've got a function that uses t as the independent variable. And we typically call the vector valued functions r. It's not necessarily a rule, but that's mostly what you're going to see. So this format, what this is telling us is exactly the same as like a set of parametric equations. And you can always flip-flop back and forth between vector format and parametric equation format depending on which one makes more sense and depending on what kind of problem you're doing. So this is technically telling me mathematically the exact same thing. My x value is dictated by the f of t, y value is g of t, z value is h of t. So one example of what this might look like, we could have 4 cosine t, -3 e to the t, and natural log of t plus 1. This is an example of a vector valued function. It is a vector because we're listing out components for x, y, and z inside of our triangular brackets, but it is it's a function because each of those components has a variable. So this would be vector format right here. But if it makes more sense to you, or based on the type of problem you're doing, you could also write x equals 4 cosine t, y equals -3 e to the t, z equals natural log of t plus 1. So these mean the same thing, and being able to go back and forth sometimes is helpful. For application problems, and if I'm going to go through this kind of quick just because we only have 40 minutes left. If anybody's trying to take notes, I will have all of this stuff available on the Moodle page. I am recording this and saving these white screens. So if I'm going too quick and you miss anything, you can go back. We also could write this in the IJK format, and that also means the exact same thing. So that's also perfectly acceptable. And these are most commonly used in application problems to represent position. So I can plug a value in for t, and it will tell me what position I am at in three-dimensional space. So let's say we've got a vector valued function r of t. Let me use the one we had. I think this is the same. 4 cosine t, -3 e to the t, ln of t plus 1. We can find r of 0. And what that's going to tell us is, one application is this is telling us position of maybe a particle moving through space. And if I plug in 0, it will tell me where the particle is at time 0. So when I plug in 0 for the t's, I get 4 cosine of 0, which is 4. -3 e to the 0 is -3. 3, and I'll get natural log of 1, which is 0. So this is a position. This is telling me at time 0, I am located at the point 4, -3, 0 in space. If we take the derivative of a position function, so if we call the original position, then the derivative of our position is the velocity of our particle. How fast it's either moving in a straight line or changing direction. Both of those are encompassed within velocity. We could also do the second derivative, which is equivalent of taking the first derivative of velocity, and what that gives us is acceleration for our particle. And we can do these derivatives just component by component. Each of our individual components within our vector valued function are going to be just simple expressions with a t variable. So taking their derivatives should be fairly simple using all the same rules that we learned in Calculus 1. The only difference is we have to do the derivative for each piece. So derivatives are taken component-wise. So if r of t is equal to x of t, no, we used h, g, and h, f, g, h earlier. Just want to stick with the same letters. So if we've got this position vector, and I want to know the velocity, which is the derivative, all I have to do is take the derivative for each individual piece, and that will give me my velocity vector. And the same thing is true for second derivative. If I want acceleration, I will just take all my derivatives again. So all this is like 3 problems packaged into one. Anything that we're asked to do to our vector valued function, we just do it on each of the components. So personally, I think one of the best applications for this is projectile motion. And if you've taken physics already, you may have already learned some about projectile motion and kinematic equations and stuff like that. But in calculus, we don't really use kinematic equations. We like to use the full position vector and then just talk about, well, how do I know it's going to be at its maximum? How do I know it's going to hit the ground? Things like that. And describe those things mathematically rather than just every single time jumping to a formula. For projectile motion, this is just going to be 2-dimensional projectile motion. So we're going to have a projectile, and it's going to start at a certain height, which we call h sub 0. And we are going to launch that projectile with a certain amount of velocity, initial velocity, and then at a certain angle as well. If we have those 3 pieces of information, then we can fully describe everything that is happening to this projectile through its entire time of flight. And the reason that all we need are those 3 values, we're assuming that this is happening under ideal conditions on the surface of the Earth. So what we know is that on the surface of the Earth, really the only thing we should have to consider is that acceleration is due to gravity, and it's pulling us straight down. So we'll have negative negative g in the j direction. And g is our gravity constant. Under ideal conditions, if you disregard all the extra little crazy stuff that could go on, The only thing that should be affecting us on the surface of the Earth is that acceleration due to gravity is pulling us straight down at a rate of g. And g can have two values depending on what system you're working in. If we are using the metric system, this is going to be 9.8 meters per second squared. If we are using the US system, this is going to be 32 feet per second squared. This is that g value there. And we're going to use antiderivatives to take this acceleration function and go backwards into a position function. We know acceleration is due to gravity. I know the angle it was launched. I know the initial velocity it was given, and I know the initial height it was launched. That's going to allow us to work all the way back to a position function. It just takes a little bit of time. So on the next page, what we know as of right now is that any sort of projectile should have an acceleration function equal to negative g in the j direction, in our vertical direction. We also know from the picture that the magnitude of our initial velocity is given. The angle for the initial velocity is given, and the initial height is given. These two go together. This is initial velocity at a specific angle. So we're given magnitude and direction. But what we need in order for this information to be useful for us, we need this in component form, because that j right there tells me that I'm going to be working with i's and j's, which are components. So we need to use this information to turn our velocity vector into component form. So you may remember all the way back from the beginning of chapter 13, the way we get an x component is by multiplying magnitude by cosine of theta. And the way we get our y component is magnitude times sine of theta. And if we're given magnitude and theta, we could very easily turn this into a v sub x in a v sub y. Right now, since we don't know those values, I'm just going to say those are the formulas we're going to use. So we know initial velocity. This is v at 0. We also know position at 0, because position was, initial position is right here. It's got an x value of 0 and it has a y value of h sub 0. This point right here is 0, comma h sub 0. That's our initial position. So r of 0 is going to be 0i plus h sub 0 j. And this is enough information for us to figure out what our equation of motion is going to be. Now, I'm never going to ask you to derive this formula. I'm just showing you how it's derived, so hopefully it makes a little bit more sense of where all the little pieces and parts are coming from. I do know that if I integrate acceleration, it's going to undo a derivative. Derivatives and antiderivatives are opposite operations. Acceleration, remember, is a second derivative. So if I integrate acceleration, it's going to undo one of those derivatives. And it's going to take me back to r prime, which is my velocity equation. So I want to integrate my acceleration function with respect to t, which means I want to integrate 0i minus gj with respect to t. The I and the j are there just because this is a vector valued function. What we're really integrating are the components. So I need to know what is the antiderivative of 0 with respect to t. And that's the exact same thing as asking what kind of expression has a derivative of 0. Do you guys know what kind of expression has a derivative of 0? No clue? It's a constant. A linear x will have a constant for a derivative. And then because a 0 constant means that the original was a constant. Because we have to do this individually on every single component, it's like 2 different integration problems. And because we're not evaluating, we have to use arbitrary constants on our antiderivatives. And because we're doing this twice, we're going to have 2 different arbitrary constants. Our I component has an arbitrary constant. And then G is just a number. Remember, G is either going to be 9.8 or 32. So what is the antiderivative for just some number here? What would be the antiderivative for 32? Whose derivative is equal to 32? And this is, Zach, this is what you were thinking on the last one. Because it's not 0 and it's an actual number, to find the antiderivative of just a constant, all you have to do is throw a variable on it. And then because we're not evaluating the integral, there's also an arbitrary constant. It's still a vector. It still has the i's and the j's. This is my antiderivative for the x component. This is my antiderivative for the y component. And we said this is going to give us our velocity equation because the antiderivative of acceleration is velocity. We also know from the information given at the beginning that initial velocity is v sub 0 cosine theta I plus v sub 0 sine theta j. So we can use this information to solve for the constants. Right now, I have a preliminary idea of what I think my velocity function looks like. I also know what my velocity function should look like at 0. So what I'm going to do is I'm going to plug 0 in to my antiderivative, and I can then set it equal to this guy because they both represent v of 0. If I plug v of 0 into my antiderivative, I'm plugging it in for t. I've got c1i. There's no t's there to plug 0 into. If I plug 0 in here for t, that whole term zeroes out, and I'm just left with c2j. Well, if c1i plus c2j is equal to this guy, the I components have to match up. The j components have to match up. That means this stuff that sits in front of them must be equal. C1 must be equal to v sub 0 cosine theta. C2 must be equal to v sub 0 sine theta. So I'm going to rewrite this vector valued function for velocity, and I'm going to replace those constants with these values here. So I'm going to rewrite this entire thing, but I'm going to replace C1 and C2. And I will have a representation for my velocity vector. So we had C1i, so v sub 0 cosine theta is our I component. And then we have negative gt plus v sub 0 sine theta as our j component. For every single projectile that's only being affected by gravity, this is the velocity function. Now we've got to go through that entire process one more time because, remember, velocity is the derivative of the position function. So if I now come in and integrate one more time, that's going to cancel off another derivative symbol, which means this will go back to position, a position function. So I need to integrate each of these components with respect to t separately. Right now this has no t's. That means it's a constant. So the antiderivative for a constant, the rule is you just throw a t on there. So we've got that thing times t is our I component. And then there's also, remember we're doing another integration here, so we need another arbitrary constant as well. So plus C1. I don't want to erase the whole thing. Yeah. And then we need to integrate the j component. So here's a t. It's t to the first. So when you integrate, we're going to add to the exponent and divide by the new exponent. We end up with negative g over 2t squared for the antiderivative. And then this guy's just a constant, so I'm going to just throw a t onto it for my antiderivative. And then we always need an arbitrary constant. And I'm almost done. I know this is kind of painful. Again, I'm never going to ask you to show all this. This is like a calculus proof. You don't need to do that. We know something about position. We were told that this guy had an initial position at the point 0, h sub 0. So that means x value is 0, y value is h sub 0 when you plug 0 in for t. So just like we did on the last one, I'm going to take what I have so far for position, and I'm going to plug 0 into that, and then I'll be able to set it equal to this to solve for my c's. So right now I'm just plugging 0 into my antiderivative for t. It will zero out that entire term, and we'll just be left with c1i. It will zero out this entire term and this entire term because you're multiplying by 0. You'll be left with just c2j. This guy and this guy have to be equal. So the x's have to equal, those y's have to equal. That means c sub 1 is 0, and c sub 2 is our initial height. So now we have a vector valued function that uses all of that information. R of t is equal to v sub 0 cosine theta. Oops, it's not doing good. T I negative g over 2t squared plus v sub 0 sine theta t. Remember the c1 zeroed out, that's why I didn't plus anything here, but c2 was equal to our initial height h sub 0. This is the vector valued function for two-dimensional projectile motion. And all these letters, we said v sub 0 was initial velocity. That has to be given to you in order to figure out our position function. Theta is the initial angle that it was launched. T is a variable. I means this is what's going on in the x direction. Remember, the g value could be two different things. It could be either 9.8 if we're working in metric, or it could be 32 if we're working in US units. T is a variable, V sub 0 we've got, theta we've got, T is a variable, H sub 0, initial height. So as long as we're given initial height, initial velocity, and launch angle, and then we can look at the units that are being used here to help us decide which G value to use. So if your initial height is given in feet, then you're going to have to use 32 because it's in feet. If your initial height is given in meters, then you're going to want to use 9.8. That way the dimensions of all of the units on all of your values match. And I've got about 10 minutes. I want to go through an example of setting up this vector valued function for motion. Any questions so far? Again, I am never going to ask you to recreate what I just showed you. It was just so you can see where this formula comes from. And it's really just a result of doing integration twice on the gravity constant.
Okay.
Okay. We are going to find the vector valued function for the position of the projectile at time t. This just means use t as your variable. If h sub 0 is equal to 5 feet, so we're launching our projectile from a starting height of 5 feet. We're giving our projectile an initial velocity of 70 feet per second. And we're launching this guy at an angle of 30 degrees. The only other piece of information that we need that I don't see here is the G value that we should be using. There is enough information given in that problem to tell what G value you should be using. What do you guys think? Should we use 32 or 9.8?
It's using 32.
We need to use, exactly, we need to use 32. Our initial velocity, initial height are given in feet. That means our gravity also has to use feet. So we're going to use 32 feet per second squared as our G value. If those were given in meters, then you would use 9.8. And those are the only two options you should ever see. So just based on the formula that we came up with on the last slide, this projectile should follow this path. V sub 0 cosine theta times t, that's going to be our I component. And then we've got negative g over 2, that's going to be negative 16 t squared plus v sub 0 sine theta, and then plus your initial height. And that's our j component. Now these guys we can simplify. You can just type those in your calculator and get a decimal. The nice thing about this projectile motion stuff is that it's application problems, so decimal answers are perfectly fine. So I love that. You don't have to worry about knowing all those unit circle values. So just a little bit of simplification, and this ends up as cosine of 30 is radical 3 over 2. I'm going to do a decimal for you guys. I don't want you to worry about the exacts. Mode. Make sure your calculator's in degree mode. 70 times the cosine of 30 degrees is equal to 60.62. So my I component is 60.62t. And then for my j component, ooh, there's a t there, I forgot, sorry. This should have a t on it. That's our linear term. For the J component. We've got negative 16t squared. And then 70 times the sine of 30 is just 35. And then plus 5. That's our J component. This right here is the vector valued function that represents the path this exact projectile will take. Now we can use that information. We've only got 5 minutes left, so I'm going to answer a couple more questions about this exact same one.
So will we eventually use the same thing and then plug in for T?
You can, yes. You can plug in for T. We can also pull these two components apart into a set of parametric equations and work with them individually. And that's usually going to be more beneficial for us. So if I pull my I and J component apart, what this is telling me is that my X value is going to be dictated by this formula, 60.62T. And my Y coordinate is dictated by the J component. So negative 16t squared plus 35t plus 5. Besides just being able to set up the vector valued function, some other things you might be asked are the maximum height and the range. Those are the two most common questions we get. Maximum height is how high it goes, and the range is how far horizontally it goes. Kind of like how long. So just a quick example for a projectile. Nope, that's not T. So there's our initial height. Gosh darn it. Here's our initial height. Right about here is our max height. So we have to remember from Calculus 1 how we find maxes and mins in order to figure this out. So in Calculus 1, this specifically is referring to height. That means I only need to use my y equation. And in Calculus 1, we learned that maxes occur when your derivative is 0. So to find maximum height, all we have to do is take that y equation and take the derivative. I would get negative 32t plus 35, and then set it equal to 0, and solve for t. So we would subtract 35, divide negative 32, and I get about 1.09 seconds. It only takes about 1.09 seconds to get to our maximum height. Now that we know how long it takes to get there, to actually figure out the height, we're just taking that time and plugging it into the y formula, because the y formula tells us how high we are. So we're just going to plug 1.09 into here, and it will tell us how high this projectile goes. Hold on, I'm going to type it in my calculator.
Yeah, you plug it back into the original, right?
Just the y part of it, yeah.
Yeah, okay.
And I get about 24 feet, 24.1. It's not very high. Okay, so to find max height, height is referring to just the y portion. We don't have to use a vector valued function. What we can use is just the y part. And back in Calc 1, we learned that maxes and mins are when the derivative is 0, so that's exactly how we do it. One more very quick thing for range. Range is how far horizontally it goes. So this particular point right here If I knew this distance, I would know the range. So the one thing that I am absolutely certain is happening at that point is that my projectile has hit the ground, which means my height is currently 0. So to figure out range, we start with setting our y equation equal to 0. That will tell us when it hits the ground. So we're going to figure out a time for when it hits the ground. Once we know the time that it hits the ground, we can just plug that back into the x equation, because the x tells us how far we move horizontally. Okay? We're going to get cut off if we aren't already. So I will finish out that video. Hey, Alex. I'm going to finish out that video and post it on our Moodle page, okay? Section 4 and Section 5 are both just formulas. Literally. Like, here's the function, here's the formula, plug it in, that's your answer. This Section 3 is probably the stuff that requires the most thinking to go along with it. All right, you guys are superstars. You lasted a full 3 hours today. I've been Thankfully, I've been recording it this time, so I can put this and the notes on our Moodle page. But I'm also going to make sure that there's videos there that actually go through everything. That way, anything that I missed during our synchronous meeting today, you could still go and find for the rest of it. Okay? I can't believe it hasn't cut us off yet. It's been more than 40 minutes. Does anybody have any questions, though, before we go? So if you want a second shot at the test, tonight is the deadline. If you haven't taken the test at all, you can do it twice today. That's perfectly fine. Only your highest score will count. So if you do it once and you like your score,